Guys, I want to code something interesting today again, and that is a disk benchmark tool in C. The reason for that is that I bought this USB stick here. It's by the brand PNY, 256 gigabytes. And this USB stick allegedly has a write speed of 800 megabytes per second. So this is the fastest USB stick you can buy for a reasonable amount of money. It's pure metal, feels super nice. I just thought instead of buying new USB sticks all the time throughout my life, I just need one awesome USB stick that is super fast. All right. And I want to benchmark it. I want to test how fast can it write files, how fast can it write data. Now for that, obviously, we have to use some benchmarking tool, and I don't want to use something that is pre-made because I think that's just an awesome small opportunity for a programming project. So let's just jump right in. I will connect that USB stick via USB. And now it's connected. You should have heard a sound right now. It's now connected and we should be able to start something. So let's start with a file. Let's call it benchmark.c and include standard.io.h. And let's include the standard IO. Obviously, we need it this time because we're going to test IO. And then we need to include standard.lib.h. No, wait, I don't even know if we need standard lib, because what my plan is to use the 0 special file, dev0, and forward it onto that USB stick, which represents any drive. You can test any drive with this. So we're writing a ton of zeros, and then we're also writing a ton of random data. And then after that, maybe we should also read data. And I'm going to use those special file descriptors. And 0 is essentially, let me show you, if we cat that file dev0, as the path already suggests, it's very useful for development. If we pipe that into xxd, which is used for representing or displaying binary data, then you see the following. That's the data that comes from dev0. So it's a special file that outputs a ton of zeros to standard out. Yeah, so we're going to write a ton of zeros in the first pass, measure that, measure the write speed, and then we're going to do the same, but with dev random. And as you can see, this is purely random data here. And obviously those two speeds will differ because writing a ton of zeros, which are, writing a ton of zeros is much easier than writing a ton of random data. So those are two meaningful values that we measure in the experiment. And then maybe we'll also do something about for reading from the USB stick. So this is a benchmark tool. We start with a main method, no arguments. And what we need is we need to access the special file. Let's check if there's something for 0 here. No, man 0. We probably need to open that file using fopen. Fopen opens a file descriptor. Let's have a look at the man page for that. Fopen expects a file name, path name, and a mode. In our case, it's just going to be read mode, because we're going to read from the file. We're not going to write to it. Writing to 0 is pointless because it's a special file. It's not going to store what you write to it. Okay, and then the return value will be a file descriptor. It's a pointer to a file structure. So let's open dev0 in read-only mode, and let's get the file pointer, or 0 file pointer is equal to fopen of that path. So that's pointing to the file, and obviously we have to type that. Or we could even call it P0, maybe that's nicer. Or PF0, pointer to file 0. Let's call it P0. Let's keep it as simple as possible. So that's the 0 file pointer, and then we need another file pointer to dev random. And let's call that one prandom. And then in the end, obviously we need to close those file pointers. Using fclose, I assume. fclose p0 and fclose prandom. All right, and now comes the magic part, redirecting the output from P0 and prandom onto the USB stick. And therefore, for that, we actually need an input argument, because we need to, of course, specify which device we want to test. So let's specify the disk argument here. And it's a constant character pointer, which is the name of the disk that we want to benchmark. Disk name is equal to argv1. And I think then what do we do next? So now we have the disk name. It's just the name of the disk. We haven't opened a file or something yet. We need to write to that disk name. The disk name is basically the path. Let's call it disk path. Okay. And then obviously we need to also check if the argument count is equal to, or is bigger than, or is not equal to 2. Then we need to print out usage instructions, because we only want 2 command line arguments. The first one is the name of the binary of the program that is being executed itself, and the other one is the name of the disk path. So we print f usage, and let's keep it super simple. Usage, name of the program, and then name of the option, which is the disk path to disk. Okay, I think now that should be good. And now, of course, the program is not doing anything yet, but I would suggest let's try to compile that into a benchmark binary. And while compiling, let's also enable all warnings using wall and even wextra. And in case we need to debug, let's also append -g. Okay, and we get a couple of warnings. First of all, we have an unused variable, which is fine because we don't use it yet. That's expected. Then there's a function main with no return value. So that's something that we definitely need to fix. So let's go down here and type return 0. That's the return value in case everything works as expected. No, but actually, if I remember correctly, we don't have to even specify a return value. So what's the warning? Wait, return with no value in function returning non-void. Line 9. What's line 9? It's this. Ah, of course, that's the issue. So here we also return 0, but we can actually omit this return 0 here. Let me show you. Yeah, now there's only a warning about the unused variable, but to keep it all aligned, let's also return 0 here. Okay, and now we can call benchmark. It will now print out usage instructions if we specify either no or 2 command line arguments. And if we specify only 1, then it will work as expected. It will step through this code right here and try to do what we tell it to do. Now, obviously, now it's not doing anything yet because we need to do something. We need to tell it what to do. So what do we do first? I think we need to write to the file, and we can do that maybe using some function that is also in the F family of functions. Maybe there's something like fwrite. That was a good guess. There's an fwrite. The function fwrite writes nmemp items of data, each size bytes long, to the stream pointed to by stream, obtaining them from the location given by pointer. Okay, so this is writing things to a destination from a source. But I think we have to read the data first. The function fread reads data from stream pointed to by stream, storing them at the location given by pointer. Ah, no. I'm not so sure about those. Fread and fwrite. What about fprintf? That prints formatted output. We actually don't need this. But my question right now is just for fwrite. We specify a pointer that we want to use as a source of data. However, we only have a pointer to data if the data is present on the heap or stack and the file that we're reading from is not present there. So maybe what we should do is instead use fget c, I think. So there are a couple of functions, fgetc and getc. I think they do the same thing. Yeah, getc is equivalent to fgetc. So, and fgetc reads the next character from a stream and returns it as an unsigned character cast to an int or end of file, on end of file or error. So those are dedicated or designed to read from file streams rather than from memory, which is probably more what we want. So I think we can use those. So let's use this. We read from P0 first. And let's store the results in a character pointer or in a character variable in C, while C is not, or C is equal to f get C from P0. And while that is not equal to end of file, we fput, there's also fput C. This is basically the opposite operation, the reverse operation. Fput C writes the character C cast to an unsigned character to stream. So that's writing stuff to a file descriptor. So fput C, and we write that character as an integer to the destination file stream. And the destination file stream is, of course, that disk path here, but we have to also open that. So let's open that file pointer. Let's call it pdisk. Or maybe I think we have to here specify the disk path, which is just the parent path of the disk that we want to perform a test on. But then we have to create files that are sitting inside of that disk directory. So for that, I have to look up how to do it. So C create file under file pointer. Creating an own file pointer in C. Is that possible? No, you shouldn't even try. That's not portable. That's for defining your own structure. File descript or file pointer in directory. Basically, I'm asking if there's a pre-made library function that allows us to create a file in a directory. But maybe there's not. C concatenate path and file name. Use string.h and function string cat to concatenate two strings. Okay, so I don't think there's something more high level here. So we probably have to do something like this. First of all, we create a pdisk path here, which is... No, we don't even need that. We just need to specify the file names. And then concatenate them with the given disk path. So let's import string.h, and then let's create a constant character pointer. And let's call that constant character pointer P0, pdisk 0. That's the file that is going to receive the zeros. Let's concatenate the disk path with the string. Yeah, let's call it just 0. Let's call it 0 dot bin, just to not risk, well, creating some odd file that is reserved somehow. I don't know if 0 is somehow a reserved keyword and it will interfere with something that I don't know about. But 0 dot bin sounds a bit safer to me. And then we create another file, pdisk_rand, and call it rand.bin. Then we open the files that are the source of the data that we want to write. And here we can now write to our destination files. The destination files are, okay, we have to create them also. fp disk 0 file pointer to disk 0 file is equal to fopen pdisk 0, and then same thing but for rand pdisk rand pdisk 0. Okay. And now down here, let's not forget closing them. fp disk 0 and fp disk rand. Okay. Okay, I think hopefully we have now created all the file pointers that we need. And maybe let's make this no, this has to be an integer because integers are returned from fgetC. And for for how many times do we write stuff to the file pointer disk 0 currently until end of file is encountered, but that will never be encountered because def0 is a special file that will always deliver zeros. But let's try it for a first test anyways. So if I now call benchmark, let's first compile it. Of course, it won't work directly. There's stuff to fix first. Too few arguments to function fopen pdisk 0. Yeah, I have forgotten the read-only no, here we need read-write. Read-write and read-write. So we need to write to those files and we need to read only from those files. Maybe actually to be very strict, we need only write access here, but okay, in a later test we need to read from those, so we can keep it at read write. So now let's compile, and there are still a couple of warnings. For example, passing argument 1 of string cat discards const qualifier from pointer target type. Wait, we have to look up the manual for string cat. I see, okay. String cat is considering the first file a destination, and the first string a destination. It's probably concatenating both of those strings and writing it into the first file, into the first string, sorry, as a result. So we can't consider that first file a constant. So let's remove the constants here just to not, just to please the function prototype. Okay, now there are no warnings when compiling. Let's see what the benchmark tool does. If we specify a file and there's a segmentation fault. Great. And before I look too closely into it, let's just hop into a debugger, GDB, and let's not waste time. And let's try to debug it. Let's run And it should give us some clue about the segmentation fault normally. I think there is some way to stop at segmentation faults in GDB. GDB, stop at segmentation faults. I think we have to specify run arguments. No, that's just the run command, sorry. This will stop at a segmentation fault, where list. Print out the values of interesting variables, the ones in the statement which got the segmentation fault. No, I'm not sure about that. I thought there was some command to halt at a segmentation fault. I know I used it before. Type where to see the stack trace and start inspecting what's going on from there. GDB will suspend your program when the seg fault signal is received. Okay, so maybe it is suspended right now. What if I type where now? No stack. Right, let me run again. I have to, of course, specify an argument. Run file. Okay, now it stopped at a segmentation fault, I think. What's where? So this is now stuck at fputc, and in my file it's benchmark line 24. Let's check out line 24. It's this line right here. So it seems like fputc is having troubles writing the character C to fpdisk0. And now it would be interesting to know what the value of C is. And it's 0. Okay, of course it's 0. But what is fpdisk0? Oh no, I don't want to quit. Print fpdisk0. Okay, maybe I have to run again because I accidentally quit something. Layout source, run file, and then we do where, and we do print fpdisk0. Maybe that doesn't work if the seg fault is already received. So, but now that we know where the seg fault occurs, maybe we can break before that. We know that it happens in line 24, so let's put the breakpoint in line 24. Let's run using a file. And I'm also surprised that there's no source code available because I compiled with -g. So there should be source gdb benchmark layout source break in line 24 run file. Okay, there we are. Now what's the value of fpdisk0? Okay, that's definitely wrong. That's pointing at the wrong thing. So why is this wrong? fpdisk0 is trying to fopen pdisk0 with read-write. That file doesn't yet exist, so maybe that's the problem. What's the value of disk path? Print disk path. Oh, okay, that's messed up. That's file /0bin/randbin. That means we have accidentally probably... of course, the concatenation is wrong. We should have read the manual. So string copy copies the string pointed to by source into a string at the buffer pointed to by destination. The return value is probably something completely different. It's probably just an error code. Okay, so let's not rely on the return value here. What we need to do is we need to good question. What do we need to do? We have the disk path. And we create a copy of it, maybe. So character pdisk0 is equal to string copy. Let's look up the main page for that. String cpy. And it's basically, it's the same syntax here, the same prototype. We have a destination and we have a source. So we need to copy from, no, we need to, what do we need to do? Do we need to allocate something? Character pointer pdisk0, and then we need to malloc. But how much memory do we need to allocate? Let's just allocate, I don't know. Let's support file names up to 100. Or even 1,000. No file path is going to be 1,000 characters. So realistically, we can even make it more explicit by saying 1,000 times size of character, but a character is just a single byte. So that's effectively it's 1,000. And then we want to string copy into pdisk0 the disk path, and then we want to come on, my Vim skills are over the top again. Okay, that's because I had the shift key pressed, the caps lock, I mean. That's always very dangerous in Vim. So here we are copying the disk path into pdisk0, and then we need to concatenate that with 0. So let's do that here, like this, and then specify pdisk0 here. Oh, pdisk0. And I think that should work. And then we can do the same thing also for the rand file. So let's just do this quickly. Let's replace all occurrences, or substitute all occurrences of 0 with rand. That didn't work. Why didn't this work? Again, 0 rand replace globally doesn't work. Maybe I shouldn't use the global thing. No, I think I shouldn't use the percentage, because that indicates that I want to use the whole file. 0 rand. Yeah, that worked. Okay. And now we of course need to also open the files, which I completely forgot. So again, let's open the files. File pointer disk0 is equal to fopen p disk0, and pdiskrand is equal to rand is equal to pdiskrand. Okay. Now, I think finally we should be at a stage where we can test something. Let me just also free the memory allocated. pdisk0, although this is not strictly necessary. pdiskrand. Okay. All right. So let's compile. Doesn't work. Too few arguments to fopen, and it's the same mistake. I need to attach, of course, the read-write permissions or access specifier. And now we should be able to compile and run the benchmark on a file, and it's a segmentation fault. So let's try layout source and put a breakpoint again in line 24. Or no, let's run this time with a file as argument and see where the segmentation fault occurred, and it's line 28 this time. Interesting, what's line 28? Let's again try layout source break 28 run file, and we are here. It's the same line, it's just shifted down, that's why. Okay. And here, what's the issue? Let's print the variables fp disk 0, and it still has the value 0. Why is no? Why is that? Let's also print C. Okay, that's expected. And let's print disk path. Disk path is file. Let's also print p disk 0. That's now a correctly concatenated file. So we did actually fix something. That's perfect. And we also fixed the other file name. So those are very... No, they are not very good. Because here I assume that... okay, I assume that the input must be a directory, but that directory doesn't exist. So probably I just have to run the program differently. I have to specify the current directory using a dot. But that doesn't work either. Layout source, break in line 28, run. No, we run with an argument. And of course the variable fp disk 0 is wrong. It shouldn't point at null. So what's fp disk 0? It's this right here. fopen. It looks like fopen has failed. Probably because this file doesn't exist. So maybe we should only... What happens if we specify we want to only write to that file? Does that change anything? I don't know. Oh yes, that changes something. So the issue was that the kernel was thinking that we want to read from that file, but that file doesn't exist. So it threw this error. Okay, so we have to consider that the input must be a directory. It cannot be a file, obviously. Because if I do this, it will segmentation fault. Because for the testing, for the performance testing, it will create files in a given directory. So yeah, okay, it must be a directory. Otherwise, it's not a valid input. We could check that, but we can also save some time. I just want to get a result that approximates something usable. So as the next step, so currently we have run benchmark in the current directory, and now it's doing something behind the scenes. We can interrupt the process and let's check. And as you can see, there are two files, 0 and rand, and 0 has been written at 601 megabytes. And rand is still 0 because we haven't written to this one, but it has already been opened. That's why it's created. So let's delete those files, remove all .bin files, and we should also remove those files here at the end of the program execution. I need to look up how to do that. C remove file. There's a call that's called remove. Well, maybe I should be more explicit and say delete file. Everyone is suggesting to use the remove function. Okay, so let's use that. Let's check remove. Remove a file or directory. Okay. I assume that the file pointer has to be closed, so let's just do this. Remove and remove. Okay, so here we remove both of the created test files. So now let's try to execute the benchmark again. Now, okay, we have to fix the warnings again. fp disk 0 is used after fclose. Okay, so it's complaining about that. Do we have to, what is the proper handling? Do we need to remove it while the file is opened? Man remove. Wait. Pointer fp disk 0 used after fclose. Yeah, but that should be fine. Call to fclose here, warning pointer fp. Because I think the file should be closed. Let's try to use the benchmark. And of course the program never stops, so it doesn't remove the bin files. So let's try to create the actual test here. We write characters to the target file. And how many characters do we write? Well, how many bytes do we write? It's more explicit that way. So one character is a single byte. We want to write, let's say, 100 megabytes, or maybe even a gigabyte. Let's write a gigabyte of data. And a gigabyte is, as far as I know, let's create 1 gigabyte of data is 1024 multiplied by 1024 multiplied by 1024. Because 1024, that's 1 kilobyte, multiplied by 1024 is 1 megabyte, multiplied by 1024 is 1 gigabyte. Now, of course, I have to make sure that this is a proper long. Can I do this in C? I think I can. And this enforces that the multiplication is really using longs. Maybe let's do this, just to be very, very sure. Okay. So we are writing characters until that's not until the end of file is reached, but until that count is reached. So let's replace the while loop with a for loop. While, and let's do it. long I equals 0, I smaller than size, I plus plus, C equals f get C from which file? From P0. And let's print up here that we are testing printf writing zeros. Okay. And then of course, yeah, we are writing 1 GB of zeros into the file, into the target file, and then we are closing that file and removing it. So let's see if that works. Now it's loading a bit. It depends on how fast my disk is, but maybe I can observe that in the task manager. We should see that the file usage and also the CPU probably are going up. Yeah, as you can see, my disk is writing at 180 megabytes or megabytes a second. And it looks like it should, oh, and down here, yeah, okay, now it looks like it's done. No, it is not. Okay, let me interrupt this just to be sure. It has already written 7 gigabytes of data, so I have messed something up. But what? So that was definitely a failed attempt. But luckily I just saved my disk by interrupting this. So what's 1024 multiplied by 1024? Ah, no, that's 1 kilobyte. That's 1 megabyte. And that's 1 gigabyte. No, it should be fine. How many bytes in a gigabyte? Ah, I was using this gigabyte rather than this. But it doesn't make a big difference. I was using a gigabyte. So let's use an actual gigabyte using 10 to the power of 9. How do I specify that in C properly? I would just do, honestly, 1000 multiplied by 1000 multiplied by 1000. And maybe we should debug this because or have I even debugged? Have I even compiled this before? Oh, the size is unused. Why is it unused? But here it says the size is used. Why is it complaining about an unused variable? Unused variable size. Long size is unused. How is it unused? It's used down here. I don't get it. Let's try to hop into a debugger and see what we can do there. Layout source. And let's break in line 29 and run. in the current directory. Oh no, it's stuck. Break. Am I stupid? How is it possible that size is not used? It is used right after being declared. Break in line, let's break in line 28. Run. And let's run in my home directory or home projects. What was the directory of this? pwd home Daniel projects disk benchmark. Okay, next. And now print the size, and this should be what? Why is there no symbol size in current context? Next. Next. Something is wrong here. Did this not compile? Did it not? It didn't compile because of an error that I didn't see. There's an error up here. Error expected expression before long, while long I equals 0. Of course, that doesn't work. Oh my god. 4. Oh god. You probably all saw it. Okay, let's try now. Programming is so much fun, guys. It's always... I really don't get how it's possible that as a human you do so stupid stuff. You keep thinking throughout the day that everybody else is stupid until you code, until you start coding. Then you are the most stupid person on earth. It's not the others, it's you. Okay, let's run the benchmark and see. Will it ever stop? Let's wait for a couple of seconds. Yes. Okay, it wrote 1 gigabyte roughly of data. That's very good. Okay. And maybe after writing zeros, we should also flush standard out to enforce that this message is written before all the other stuff, because here it somehow printed this after I was done. Or maybe we should just print a new line. Maybe that forces writing zeros. Let's check. No, it seems to be writing stuff and only then outputting writing zeros. So maybe we have to use flush to force standard out to flush its buffer. Damn it, I forgot compiling. So ideally I need to compile and execute right away. Yeah, it's now writing zeros and printing that out, but maybe it's also printing it out with a new line already. Yeah, okay. It's working. Now it's writing zeros, and we know that it's writing 1 gigabyte of zeros. And now all that we have to do is we have to stop the time. Linux or C get milliseconds. Let's have a look how that works. That's too complicated. What's the simplest way to do it? Get time. Get to current time in C. Get milliseconds. We could also, of course, also super over-engineer it and code a stopwatch, but I think that's not worth it. I mean, just getting the milliseconds and then getting the stop milliseconds is more than enough. So we can include system time, and then we get the time value, then we get the time of the day, then we get the seconds, and we get the seconds too, probably the something else. We could also, of course, use only seconds, but that is probably not so accurate. There's the time function, but it returns seconds, not milliseconds. If you need greater precision, you can use platform-specific tools like Windows get system time as file time, or Unix get time of the day. So if we use seconds, maybe that's good enough. But the faster the disk is, of course, the worse the precision is. But all those solutions are very complicated, so let's just use the simplest solution. I mean, we don't want to create something super fancy. And maybe instead of tracking more accurate time, we can also just write more data, which also improves the accuracy of the result. So this is a time t structure that we get by using time, the time function, okay? Okay, time gets the time in seconds. It returns time underscore t. Returns the time as the number of seconds since epoch. Actually, it doesn't matter what the reference time is because we are just going to use a delta time between start and end. On success, the value of time in seconds since epoch is returned. On error, time t minus 1 is returned. Okay. Yeah, sounds quite simple actually. So let's create a time t here. Start time. Or we can even make it more C-like, because in C everybody wants to code hard to read code and call it TS. And the start time is the time right now. And again, what's the argument to that function? It's a pointer to a wait. We have the option to provide a memory pointer here. We don't need to. We can also use just null. That's nice. Okay, that's the start time. And let's create the end time down here. T end. Or we don't even need an end time. We just need a difference, TD or delta TD. So that's the current time minus TS. And then we can print the console. Took seconds. Took 6 seconds. How nice is that? That's good. So the time tracking works. And now we just need to calculate based on that time. We need to calculate the bit rate. And we can store that in a double probably. because we need a floating point number, or it can even be a float, lower precision, doesn't matter. Let's call it speed, and the speed is equal to the size that we transferred over the given delta time. And we have to ensure that this is a floating point operation, so let's cast it to float. Let's cast size to float and divide it by TD. Let's see what the result of that is. Writing zeros. And we don't get a printout, obviously, because I forgot that. Took 6 seconds. Let's print out the results here. Write speed is equal to this, and then new line. And this needs to be a floating point number, so I think we can use F with a precision of 2 digits after the comma. Okay, let's see. And obviously that speed is measured in bytes per second now. We don't want that. We want to divide this by 1000. That is kilobytes per second. And then divide that by 1000. That is megabytes per second. Megabytes per second is good enough for today's technology. Let's see what the result is. Yeah, okay. And of course my formatter doesn't work here. As you can see, this prints out the number, the fraction, 0.2, and the 0.2 is this thing right here. Of course I have to write that format specifier somewhere else. Wait. I think I have to use this. Let's wait for another 6 seconds to see the result. Now it should work, I think. Yes, okay. And then we attach megabytes per second. And then once more compile. It's now writing zeros to the disk. Now it's still using my own internal disk. It's quite fast, as you can see. And the result is always very, very much the same. Interesting. Okay, and this is now, this entire block here is measuring the time based on a given algorithm, based on a given source file pointer. In this case, it's using fdisk0 as a source file. Now we can just copy that entire block and extract it into a new function. And let's call it test file pointer. Takes as input a file pointer, fp, which is the source file of our data. And then we paste all of that. And this is basically now a reusable test method that we can use to perform the measurements. So this is the source. And this is the destination. And we get characters from the source file and we write them to the destination. And I think if we call test fp here, then we specify the source. The source is p0 and the destination is fp disk 0. And then we can do the same thing and do p rand, and the destination is fp_disk_rand. And then it should of course also print out accordingly, because here the write speed is, no, it's generically measured independent of the file. Maybe we should do something like printf testing zeros, and then another printf testing random numbers, testing write zeros, and testing random numbers, also write. And let's see if this works if we compile. It doesn't work because probably there's an error somewhere. Yes, prand is undeclared. What is prand? It's called prandom. Okay, it's testing zeros, writing zeros. Why is that a wrong output? We need to remove this printf statement here because this function is not specific to zeros anymore. And also I want to rename all the test fp function calls to benchmark, because this is now more applicable to our use case. So because we're performing actual benchmarks, disk benchmarks. Let's see. So we're now testing zeros. We get a result, and then we're testing random numbers, and technically this should be lower now. Yeah, as you can see, this random number writing is slower. But the file still persists here. That's bugging me. Do we need to remove the files while the file pointers are still open? That would be a surprise to me. Let's try this. No, it doesn't seem to remove the files. I don't know why it doesn't remove the files. What is the function that I call? I call benchmark dot, so I call it with the current directory as an input. That's surprising. Oh shit, I just removed all. But luckily I can recover if I save the file in Vim again. Oh god, I just almost deleted all of the project. I deleted it, but I was able to recover. Oh god. Okay, let's compile and test again. But actually I would expect the files to be removed here. They are created but not removed. What is wrong with the removing of a file? Remove deletes a name from the file system. It takes as input a constant character path name. And I was inputting file pointers. Now that's dangerous. What if it was actually by accident just a slash character or something? I could have really messed something up here. So this input should be pdisk0, which points just to the string rather than the file pointer. Okay. Let's try again. Oh, and now there's some issue. There's a warning about the format. D expects argument of type int, but argument has type time. And time is a long integer. So here we have to use LD. Okay, that's a good warning. Okay, let's try again. All right, so this is now measuring the write speed to the disk. And I think for the scope of this video, this is enough. So now we are writing something to the disk and then checking out how fast it's being written to. One more detail that we could do is we could make the number of gigabytes to be tested variable, because the more gigabytes we test with, the more precise the result will be. So we can, in the main function, expect an argument count of 3 and call and rename the usage to number of gigabytes, and then a path to disk directory. That's important, otherwise it won't work. And then the number of gigabytes will be used in the benchmark as the first input argument. So here we create a new integer gigabytes variable, and that is equal to a to I of argv2. That's the second command line argument. So we have to have 3 total command line arguments now. Well, 2 positional arguments and 1 is the program name itself. And then we pass into benchmark the gigabytes as a number. And also we do the same thing up here, int gigabytes. So and the size is then gigabytes multiplied by 1000 multiplied 1 blah blah blah. You get the point. And I hope this properly converts to a long, because gigabytes is an integer. Control reaches end of non-void function, line 20. What's line 20? Let's just return, no, the benchmark is actually only printing out stuff, so let's make it return void. And let's try again. So now this is outputting the usage instructions, benchmark, number of gigabytes, and path to disk directory. And now we can use that benchmark in the current directory. Or no, we want to test, let's say, with 2 gigabytes in the current directory. And this doesn't work because probably, of course, no. We need to specify the number of gigabytes first and then the path to the disk directory. That means the disk path needs to be the second argument, or well, the third in array access indices, and this needs to be the first or 0th, well, no, the first argument. Let's save this. Okay. Let's compile first, of course. No warnings, that's a good sign. Let's run this test. 2 gigabytes tested on the current disk. Write speed is still 166.67 megabytes per second. And random number write speed is, let's see, 125 megabytes per second. Now, obviously, the timing is not so precise, so maybe I should improve that. No, I will improve the timing. The timing is really bugging me. So let's get the current time in milliseconds. Get time in milliseconds here. Try using microsecond resolution with time val. Okay, let's include system time and delete the other time. And then we call this. Okay, we get time values here, and then we access time value seconds. And then we have microseconds here as well. The U stands for micro. It's like the mu Greek character for micro. Okay, let's copy that code and create a function. Long get micros. And let's paste that code. Thanks to the open source community for creating that code so that I can rip it off of you. So here, get time of the day. Let's call that time now. The current time of the day is also stored in now. And then we don't need to print it out. We just need to we need to return. TV time value seconds and time value microseconds. Well, this is of course dangerous because we're dealing with really large numbers, so there's always the risk of overflowing the variable's size. Micros is equal to now TV seconds multiplied by 1000 multiplied by 1000. That's converting it to kiloseconds. Oh god, I'm getting tired. This is converting it to milliseconds. Kiloseconds. Yeah, actually, what? No, that kiloseconds doesn't make sense. Why does nobody in this world use kiloseconds as a unit of measurement? And this is converting it to microseconds. And then we add on top now TV USEC for the microseconds. And then we return the micros. Okay. And in the benchmark method, we can now use those micros as our time measurement. So long micros is equal to get micros and let's create the difference measurement here, long. Delta time is equal to get micros minus micros. And then we can print out took so many seconds. How many seconds is that? Actually, we don't need to care. Yeah, but we can still print it out. Wait. Delta time. And let's also make it explicit that delta time is stored in micros. Actually, I much prefer writing out variables explicitly like this. So previously we stored variables as this because for example, TD, time delta, but I hate this. This is so illegible, nobody can understand it. But this seems to be a phenomenon in the C community somehow, or even in the Linux community, or even in the open source community overall, to make stuff ridiculously hard to read because it's somehow cool. I just like to write out things such that everybody can understand it. So to get the time in seconds, we just divide the micros by this number. This is 1 million. Because 1 second is 1 million microseconds. Let's see what the code now does if we execute it. So let's benchmark 1 gigabyte in the current directory. Of course it doesn't work. Conflicting type for get micros. Where's the issue? Okay, first of all, let's fix issues top down. Let's start with the errors. TD is undeclared. Okay, what is TD? TD is this time difference. Now we have to replace that with delta times seconds. And actually, yeah, okay, let's just use that. Delta times seconds. And I think we can make this, since this is not going to be an integer number, this is actually going to be a floating point number. So let's make sure that this is properly divided here. Oh God. Data type hell. So next error, double, what's the name of that? Double speed? No, what was that? It's the delta time seconds. Next error is delta time is undeclared. Obviously, we have to refresh it, rename it to delta time seconds, and we have to say that this is a double. So it's a floating point number, I think. Okay, that works. And now the next error is conflicting types for get micros have long int. Line 23, get micros. Okay, so wherever I use get micros, I declare it as returning long. So what's the conflicting type here? Previous implicit declaration of get micros with type int. Is there some library function already defined for get micros? Wait, let me just do get micros. No. Get micros Linux. No, but this looks like there's get micros somewhere defined. Of course, I'm using it up here, but the function is only defined or implemented down there. So let's move it up here. And that should solve the issue. Okay, now we only get a warning about the implicit declaration of function get time of day. Why is it implicit? It's because that is declared in system time, not in time. Okay, now it seems to be working. We are testing zeros in the current directory. took 5.83 seconds. Write speed is 171.61 megabytes per second on my main hard drive. And testing random numbers is this. Write speed is 128.12 megabytes per second. And the files are deleted. All right, so this write test is now working. That's awesome. That means we can now prepare for a final test on my magic super fast USB stick. Now, of course, it's possible that my code is not super efficient and is maybe even introducing artificial delays because I should be piping the zeros directly somehow instead of looping. But yeah, for my first little benchmarking tool, I think it's nice. Okay, let's keep it that way. And let's refresh the documentation here. X gigabytes of data. Okay. Now let's move the benchmark test here. Let me just compile one more time, and now we can do a final test. So the benchmark tool works like this. We have a binary that's called benchmark. And by the way, I make that C file available on my private GitHub repository. You can get access to it by becoming a Patreon. So let me git add that and git commit create disk benchmarker and git push. All right, so the file is now made available to all Patreons. So now let's do a final test with the compiled binary benchmark. I want to test 1 gigabyte of data for a first test on my USB, on my super fast USB stick. Now this is my USB stick. Let me get the path by hitting Ctrl L. This is the path of that USB stick. So let me copy that path and paste it here. And let's see what's happening. Now it's writing zeros, and we should see the test files here being created, and it's measuring the write speed now down here. So the write speed is 152 megabytes per second, and the write speed for random numbers is 117 megabytes per second. What does that mean? That means that the limitation of the data transfer is probably not. It's probably the code itself. So this code is, as you can see, it's spiking the data transfer rate, but it's not maxing out the performance. So this data could be transformed, it could be moved at much higher speeds if there was no inefficiency here. So somewhere something is taking too long time, and I think proper disk benchmark tools such as DD, let's have a look at DD, they read and write multiple bytes as blocks, as entire blocks. And what our benchmarking tool is doing is it's effectively looping over individual bytes and moving them. That might be not the most efficient thing to do. And there is for sure a better way to do this. What we're doing is we're reading individual characters and putting them to the destination file. Now we could optimize this. For example, for the zeros, we know that every single character has the same value. It's going to be 0. So we could omit the reading from the source file and just hard code in fputc that we want to fputc 0 destination. Something like this can be optimized to really max out the writing speed that your benchmark tool can produce. But this is, I think, a very nice first test for benchmarking. Let's try the USB stick. Let's try 3 gigabytes of data on the USB stick and observe the system monitor again. Now, as you can see, the file transfer rate is, or the data transfer rate is spiking. And by the way, even in this test, the USB stick is really, really fast, because which USB stick supports 160 gigabytes of data transfer. So even with our inefficient test, the test files that are written here are written there very, very fast. And I think that just shows that picking the right USB stick is very important. So traditional USB sticks, such as this regular Intenso one that I have here, you probably have seen this model before. This one writes at, I think, 5 megabytes a second. And yeah, we can do another test actually that just shows that this USB stick is incredibly fast by generating a large random file, for example, by catting dev0 onto our media USB stick. Oops, let's properly copy this. And let's cat zeros onto this path into a file test. And let's observe the speed now, writing raw onto that USB stick without any testing software. There's the test file being written right now. And let's check out the system monitor. And here you can see that the disk write speed is now 330 megabytes per second. So it's much higher. And that's because probably our C code has an inefficiency. And of course, as I already explained, it's because we pick individual characters from the source file stream and write individual characters to the output destination file stream. So, and this is proving that this USB stick is super damn fast. And now we can compare it. By the way, let me actually delete that file that we just created. It's probably 10 gigabytes in size by now. As you can see, the deletion even takes time. Let's compare this super nice USB stick with another one. So okay, now I unplugged this super fast USB stick here. This is it again. Solid metal, super nice quality, feels heavy in the hand. I don't know why it doesn't focus. Come on, focus. Anyways. Yeah, now it's focusing. So that's the super nice USB stick that we just tested. 330 megabytes of write speed in practice, and advertised it was 800 megabytes. Depends probably on what exactly you write and your system, of course. It seems that in my system it's 330 megabytes, but if you have a super high-end system, it's probably much faster. Now let's perform that same test on the other USB stick. So let me just, that's an encrypted drive. Let me can I format it here? No, let me pick another USB stick. This one, another regular Intenso USB stick. So let's see. Yeah, and that's my Linux Mint installation USB stick. So let's pipe data onto it. This is the path. Let's do the same test with an updated path now. Test and see the write speed of that in the system monitor. And that write speed is, as you can see, much lower, and it's also spiky. So on average, it's writing at 5 megabytes per second. So that's really interesting behavior. As you can see, the high quality USB stick had a constant rate of 330 megabytes per second. It was a flat line. And this low quality cheap USB stick, of course, every USB stick is good as long as it fits its purpose. But this one, the one that I'm writing to right now, is probably used for whatever Word documents and PowerPoint presentations. This one has a completely different data transfer profile and is transferring at way lower transfer rate, even though it's plugged into the exact same USB slot. So that just shows that you have to pick your USB stick wisely. Guys, I will link this USB stick in the description down below. It's really incredibly fast, as you've just seen. And this can be very, very useful when you, for example, want to save movies on it, and you plug that into your TV, and you can just stream the movies from the stick directly, and the video files will play flawlessly as if it was stored on the native internal hard drive. Right. So that's what good USB sticks can do. And of course, you can also use this to burn a Linux ISO or any operating system onto it, and then use that as just like an SSD to run your computer off. This thing is way more than fast enough to run your entire computer off. So it's just awesome. You have so many uses for this. So run your operating system off the USB stick, watch movies in 4K off the USB stick, transfer data from one computer to the other using this USB stick, do whatever. It's super fast, super nice. So I can highly recommend getting a really fast USB stick. And that's actually, so now I'm talking a lot, but that's actually one of my base philosophies of life. It's that when I get a product, I want a simple product, but that must be super nice. For example, I bought, a couple of years ago, my girlfriend asked me what I wished for as a gift on my birthday. And I just said, I just want one really good pen. And I wished for one specific one, and it's this one. And as you can see, this is a solid metal pen. This is just a regular pen. It just writes as any other pen. But this one's indestructible. This one will last a lifetime. And that's what's so awesome about it. And I love simple products that will last a lifetime because they are so durable. Have a look at how it sounds. So this is solid metal. And I just love quality products, even if they're simple. And this thing is cheap. It's like $10, 10 euros. Nothing spectacular. But instead of owning 20 plastic pens, how about owning one single solid metal pen? And the same thing applies to USB sticks. Instead of owning 10 super slow USB sticks like this one, writing at 5 megabytes in this spiky data transfer profile here, well, how about just owning one super fast USB stick? I link it in this description if I find it. And aside from that, I wish you all a good rest of the day. Have a good time and see you next time. Bye-bye. Guys, okay, this is an appendix to the disk performance or disk benchmarking tool that we just coded. I think I know the issue. The issue is that currently we, as I also said previously, we iterate over every single byte in the source file and then put that byte into the destination file. Now that is not efficient at all. What we can do is we can indeed use the fwrite function and the fread function, both coming from standard.io.h, to read and write bigger chunks of data at the same time. So let's try to use those instead of this individual loop here, and see if that improves the performance. But I just saw online that someone used those when copying files, and allegedly there was better performance. So I want to try it. So what we have to do is we have to first read from the file. We have to call fread. We read into some memory. No. This is what is this? This is a pointer to nmemb, items of data, each size bytes long. So this is the memory. Okay, and this is the size. The size is the number of members, and then nmemb is... no, the size is the size per member in the memory, and then this is the number of members, as far as I understand. So basically, this is just a pointer to some memory. Then we read size bytes and number of members from this stream. I hope I can remember that. So we read into some pointer size bytes. Okay, so here, oh no, how do we do it? We should somehow decide for a chunk size. The size is depicted in size t, so let's create a variable for that. Size t is, I think, the same as an unsigned long, or it's a big variable type. I think it's a 64-bit unsigned integer. And let's call that the chunk size, and the chunk size in our case is 128 bytes. Arbitrary choice, you can pick any size here. And now we have, instead of getC, instead of calling getC, we have to call fread, and we read into, now we have to read into a 128 byte buffer. Now for that we can allocate something on the stack or on the heap, it doesn't matter. Let's just allocate something on the heap. Let's call that the buffer, and the buffer is chunk size bytes. So we read into buffer chunk size, one element of that size. So one block of 128 bytes, and then we specify the file that we read from. The file that we read from is the source file. And then we do the same thing in reverse. We just write something, but we have to look at the return type here. This returns a size t, and the size t is the number of items read or written. This number equals the number of bytes transferred only when size is 1. Yeah, of course. If size is 1, it's the number of bytes, yeah. Otherwise, it's the number of items read or written. Or the end of file, or the end of the file is reached, then the return value is a short item count or 0. Yeah, so basically this tells us how much was read, and in our case, it should be one element, I think. One element of size 128. So number of chunks read is equal to this. And let's create that variable up here just to improve the performance a bit. and assign it here. And then we do f write, and we write we write from the buffer. Yeah, from the buffer into the file pointed to by stream. Basically, it's the same operation. And then that returns the size t, the number of items written. But we don't need that, I think. So we write from buffer chunk size 1 into the destination file. What's the destination file? Dest. All right, and that should be it. Let's see if we compile this. Oh, this doesn't work. The number of chunks read is not used because we hardcode the 1. So we don't actually need it. Let's discard it for now. And let's try to compile this. There's still a warning. Expected constant void pointer, but argument is of type integer. What? What did I do? Where's that integer? Int c. Wait. Where's the int c? It's up here. And of course, there's still a big bug in the code that we will address in a second. So what's the issue here? Is this just a warning, or is there an error? Oh, there's an error. Variable or field buffer declared void. Wait, what? Did I declare? What did I do? This must be a void pointer. I don't even know if you can declare it that way. Oh, you can. Yeah, because we don't care what kind of data type is inside that. So we compile benchmark 1 GB here. And let's see if this changes the speed that we benchmark with. Oh, I have to interrupt this. I made a mistake. Let's remove the files. I accidentally just wrote 15 GB of data. I am doing this 128 byte chunk reading and writing 1 billion times because I loop until size is reached, which is not applicable anymore. Of course, now we have to divide size by the chunk size to get the real number of chunks that we have to loop for. So technically we have to do, we can make this a while loop. We don't need a for loop anymore. Or we can do a super cool for loop. So for, we don't need a counter variable. And the condition is, what's the condition? Or maybe we do need a counter variable. We need the counter variable. Okay, we need a counter. But maybe, is there not a better way? So we know the size and we know the chunk size. Yeah, let's just derive the repetitions. And the repetitions are, of course, the size divided by the chunk size. Reps. And then I think this is fine. Let's see if this works. No. I need to interrupt it. I forgot to compile. So I was almost blowing up my disk again. I hope in the scope of this video I don't destroy my disk somehow by filling it up to the last byte. Oh my god, this is risky as hell because I am not paying enough attention. So I compiled. There's no warning. That means now I can run the benchmark. Let's see. Oh, and now you see it's much faster. Now I have 1 gigabyte of write speed on my current SSD, and that's the solution. That's much better. So write speed for zeros only is 1 gigabyte, and write speed for random data is 348 megabytes. If we do, by the way, the files did clean up. Let's check the same thing for 10 gigabytes. Yeah, okay, that works. Awesome. Of course, the 10 gigabytes of random data will take a bit longer, but now this is testing my current SSD that's mounted inside my computer. I will test the USB stick now again. And actually, we can now do a comparison between the high performance USB stick and the low performance USB stick. So let's try to benchmark the low perform. Oh no, we can't even benchmark the low performance USB stick because its write speed is actually just 5 megabytes per second. So if we benchmark it with the minimum of 1 gigabyte, then that will take 200 seconds, which leaves us waiting here for a couple of minutes. Okay, so let's just benchmark this one. And I want to benchmark, let's say 5 gigabytes or 3 gigabytes on, and that's the high performance ultra fast USB stick. Let's see how fast it is. And as you can see, it's super fast for a USB stick. It's crazy. Yeah, this is awesome. So guys, this is how you code a benchmark tool in C. Obviously, we spent a lot of time with the basics here, but I find it quite nice that we discovered what the fundamental issue with our benchmark tool was. And now that we've solved it, we can do pretty awesome write speed measurements with our own tool in pure C. How awesome is that? All right. See you next time. Bye bye.